Alright, our last video is going to talk about the uses of radioactive isotopes. You can think of this slide here as a table of contents as we go over our 4 uses that we will be covering. Our first is determining the age of natural things, so this is dating. We use tracers in chemical reactions and industrial processes. We use them to diagnose and treat diseases, and we also use them for providing sources of energy. So starting off, let's start looking at dating. So again, I'm going to use them to tell how old something is. This is called radioactive dating. Not all atoms are going to decay at once. Again, this happens spontaneously throughout the material's existence. It's going to happen randomly. We cannot predict this. But we can measure when half of the elements will go through decay. This idea is called half-life. So when we have a sample of material, the time it takes for half of that material to go through radioactive decay is called a half-life. And again, this is cutting things in half. So this is exponential decay, which means we're never actually going to theoretically get to zero. You always just keep cutting things in half, cutting in half, cutting in half, and so on. So going a little more in depth, again, half-life, length of time needed for half of the items in a sample to go through decay. It's going to be different for each type of isotope. For example, they hear a lot about carbon-14 dating. Carbon-14 has a different half-life than, say, nitrogen 16 or whatever. Right? So first we got to figure out which element we're talking about. A lot of times we use carbon. If not, we kind of move to potassium and other elements as well for longer periods of time. So it is different for each different isotope. They range from less than a second to billions of years. So depending on what element I'm looking at in my sample, I can determine whether it was just a few weeks old or whether it was up to billions of years old through this process. All what matters is which element I choose to look at. You should probably reference page 143 for a little more in-depth on this topic. Radioactive dating. So a lot of times we use by measuring carbon-14 in organic material because carbon does make up all organic life. After it dies, it's going to stop taking in carbon. It needs to take in and replenish its carbon while it's alive, but once it's dead, all its processes cease to exist, so it's no longer going to take in carbon. So I can look at this sample and I can say, well, okay, this is how much carbon-14 should be in there. And then I'm going to look and see how much carbon-14 actually is in there. And I'm going to count half-lives of carbon-14. And each half-life is so many years. If I have 3 half-lives, then I've cut my sample in half 3 different times. I just count 3 half-lives, which is a certain amount of time for carbon-14, and it gives me an estimate of how old this object is, this sample is. So whether that is fossils or even rocks can go through this. Older dating, because carbon-14, again, we could use radioactive dating from any time period between a couple of seconds to billions of years. Carbon-14 really is only useful up to 60,000 years. After that, I need to use other elements such as potassium-40 or uranium-238. Our next use for radioactive material is tracers. Tracers are chemicals that I inject into different environments to see where they use that chemical. For example, if I want to find out where a plant uses phosphorus, because I know phosphorus is not part of photosynthesis, so why does a plant grow better with phosphorus than without phosphorus? Again, phosphorus is found in a lot of your fertilizers with nitrates. So we're going to put phosphorus into this plant, certain phosphorus, phosphorus 32 to be particular, is going to be radioactive and it's going to start giving off gamma radiation. So I'm going to start looking for where that gamma radiation is coming from, and then it's isolating parts of the plant that use phosphorus. Another way tracers work is for detecting weaknesses in metals. I apologize for my picture. This word right here under here is metals. So gamma ray is going to detect weaknesses in metals. So let's say I'm at an aluminum plant and I need to make sure my sheet of aluminum is uniform throughout the whole sheet and not just kind of thicker in the middle and thinner on the sides and has defects, because I mean on this piece of aluminum could go into an airplane and that defect could change the air resistance and flow of that airplane and cause it to crash. I got to make sure my aluminum is uniform. So what I do is I shine gamma rays through it. And again, gamma rays will develop photofilm. So if I put a piece of photofilm on one side, put gamma radiation on the other, it goes through my aluminum and it develops the film. Well, wherever it developed more film, there's weaker aluminum. And therefore I know to adjust the way my plant is producing aluminum to make it more uniform. We can also use this to detect how much wear and tear different infrastructure has. So for example, if I have a bridge that's really old and it's starting to crumble, well, which pieces really need replaced? I'm going to shine gamma radiation through the I-beams and structures of it and see which ones are actually weaker, so I know where to reinforce them if I don't have the ability to just replace the whole bridge. Next up is medicine. A lot of you are probably familiar with chemotherapy with cancer. So I guess I am starting at the bottom here. A lot of times chemotherapy is going to be using cobalt or iodine and different isotopes of it. Again, it has to be a specific isotope of cobalt. So let's say cobalt 60 is going to go through radioactive decay, and therefore that gamma radiation it gives off, I'm going to use that to destroy my abnormal growth of cells, because that's what gamma radiation will do if you're exposed to it. It destroys your cells. So if I can concentrate that into one area, then I can start destroying my cancerous cells. Of course, gamma radiation does not know how to tell which ones are not cancerous, and it's going to destroy all of them. And one of the reasons why people don't necessarily feel too great after receiving chemotherapy is because that gamma radiation is just tearing through all of them, not just the cancerous ones. But it is, some cases, it's better than living with cancer. We could also use different tracers to determine different problems with your bones, your kidneys, and your digestive tract. So a lot of times before you go into surgery or something, the doctor gives you a little liquid thing to drink so it can process those tracers, and then you can see where the problems are actually being defective in your body. So before surgery, we can go in and fix the actual specific areas that are the issue and not just replace everything. Our last one is power. I guess uranium-235 is this number here, 235. That's our uranium isotope that provides nuclear power. The Simpsons, Homer Simpson, is our nuclear engineer. He doesn't do the greatest job, but it does give you an idea of what nuclear power is. It is a power plant. It's actually a very clean source of energy. Whenever you see these giant cooling towers, is what they are. They're actually shaped so it is a giant cooling tower. And it cools the air as it goes up. This here is actually water vapor condensing. It is not carbon dioxide. It is not harmful gases. It's actually a pretty clean source of energy. And if protocols are followed and people are up to OSHA standards and everything, it's actually a very safe form of energy. It's also used in nuclear submarines, so we don't have to keep refueling submarines. They have kind of their own nuclear power plant in there. Problems with it is when you do not follow safety guidelines and stuff and it decides to blow up, you get things like nuclear weapons from it. Or you get what happened in Chernobyl, which is a city in Ukraine where its power plant went through nuclear meltdown and kind of blew up. Chernobyl is now currently being re-inhabited, but in more recent years, like in 2011, when the giant earthquake off of Japan struck and caused a huge tsunami that took out one of their nuclear power plants in Fukushima, the whole area was evacuated, and people are still not welcome into that area because of all the leaks and waste from this radiation. It still affects them, and again, you don't really want to be exposed to them. The one other downfall with nuclear power is we do have waste. We do get nuclear waste, and these things have an extremely long half-life, so they're not going to go away. You can't just throw them anywhere. People might stumble upon them, find them accidentally, not know what they are, and be exposed to it and expose others to it. You can't just dump this in your water system and have it run through all of civilization and the oceans and the wildlife and all that. So really what you need to do is you need to bury your nuclear waste and hope that nobody in the future decides to dig in that spot until the half-life is actually up, and it decays on its own. We do use protective clothing and different monitoring techniques when dealing with this stuff. Again, your gamma radiation penetrates a lot, but it's all about moderation and how much you're being exposed to for how long, which one of our videos talked about.